I'm a tennis player, a dog trainer, a lover, a neuroscientist, and a cook. And let me tell you right now that no matter which of these pursuits you pursue, you have to have your equipment in good shape and know how it works. Suppose, for instance, you want to make ice cream. You have to have ice to make ice cream, and you have to know how to make ice. And you make ice in one of these things. It's called an ice tray. And you just can't pick up any old ice tray. Note that this ice tray is not quite straight. It's not quite even with the table. You have to measure that, and then you have to correct for it. So, dial in, checking as you go to see if it fits. It still doesn't fit. You can tap it down a bit. There we go. Now there's an ice tray we can use to make ice cream. So you see, the lesson is you have to know your equipment and take care of your equipment. So let's turn to neurobiology. As the great story unfolded this year, we saw a fine example of understanding your equipment. As we proceeded from quarks and gluons, it became clear that you're never going to understand the brain without a thorough understanding of quantum gravity, if even then. The J guy, by his own admission, did not present an adequate presentation of Fermat's principle, which we will see later in this presentation, lies at the very heart of EP. The point of this educational tape is to present in more depth the derivation of Fermat's principle and to see how it crosses a bridge from physics to biology and becomes the very basis of LTP. In order to carry this out, I'm going to have to enlist the efforts and help of my good friend and colleague, Mark Terasaki.
Fermat looked at this thing, and this kind of pad like this, and said, well, this is, you can explain this by saying that you can get the same equation if you're trying to minimize the time that you're going from this point to this point, given that n1 and n2 is the speed that you're traveling in this part or this part. So that's the principle of least time.
You know, Mark, I would really like to think of a way to relate the principle to LTP.
What principle?
Fermat.
Oh, principle. Oh, right.
Gee.
Principle and LTP? Wow, what a strange combination. Kind of a connection between physics and biology somehow?
That's it, Mark. I feel that the mammalian brain, through evolution, has developed a way to use LTP to create a hyperpresence.
Wow.
And it's in that hyperpresence that the principle is operating.
That sounds great. Tom.
Yeah, and I know how to test it. I think I have a way to show this.
Let's go.
Let's go! Explicit harbor was the placement of a set of poles along the beach at 10-foot intervals, and another set of poles going out into the ocean, also at 10-foot intervals, except for the last one, which is a 5-foot interval because it got too deep, which is Jennifer was laughing. The idea now was to start the dog here and to pursue a ball here. And it would be a mighty dumb dog that would do this. The question is whether he'd go the fastest way and go a certain distance along the beach and then turn and reach the ball this way, as predicted by Fermat's principle. Let's see what happens.
It's around on 2. Yep.
Go back. Right at that stake.
I'd say a couple feet this way. Good dog, Watt. All right, we got the experiment done. And Jennifer and our assistants, Watson and Wicket, performed many experiments over the summer at Clifford Harbor. And we've shown you on the videotape an example of one experiment, and I want to show you here a plot of the results of this experiment. The first phase of the experiment is walking. The second phase of the experiment is waiting. And the third phase of the experiment was swimming. We hadn't expected to find waiting. We thought we would go directly from walking to swimming, and there would be a simple dyadic problem. However, now we see we're faced with a triadic problem, and I hope that Mark is going to be able to deal with the additional mathematics.
B2 sine theta 1 plus B equal to B2 sine theta 2. And it turns out that the triadic nature of this phenomenon does pose some problems, but I think that it's not so bad. So if we make that calculation for this part of the problem, we come up with 7.5 and 12.7. Not so bad. But if we do this part of the problem, from here to here, we come up with 2.9 to 3.1. That's pretty good.
Good, Mark. That must mean that Fermat's principle is at the very fundamental basis of LTP. Hope that as a result of these experiments, you now have an intuitive feeling for the fundamental nexus of physics and biology. And we'll look back gratefully to those long hours of physics lectures in the Marine Resources Center. We know you will find these lectures useful when you return to your lives. Just remember always to keep your equipment in good shape, and to always find the path of least time.